No, it will come independent of m. So Sujal, that's the interesting thing. Mass will cancel out in your equations. Okay. Just start the question, you will understand. Okay. Make the free body diagram correctly for uh, the journey upwards. Do that and you will understand how we will be able to. Yeah, so that is the main thing, Pratyush. You have to understand that kinetic friction, by definition, always opposes slipping. Okay. So how will it act when you are forcing the object to slip up the inclined plane? It will act in the direction opposite to the slipping. So remember, kinetic friction does not act according to external force. It acts according to the direction of slipping. So it doesn't matter that the external force is the tangential component mg sine theta is down the inclined plane. It does not look at that. It looks at where the slipping is occurring. Isn't it? That's the logical thing, right? If it is slipping towards the right, then friction will act towards the left. If it is slipping towards the left, then friction will act towards the right. It doesn't matter what the forces are. No, it is opposite velocity, beta. Pratyush, the direction of kinetic friction is opposite to the direction of velocity. Okay, so that is the important thing over here, that kinetic friction, mu k into n, that will be the kinetic friction, opposes the slipping. Yes, Dhruv, that is correct. Dhruv and Devansh, both of you got the correct answer. Parth, your answer is also correct. Very good. So you can proceed to the second part, all of you. So if you do a comparison of the situation where the block is sliding up the inclined plane versus later when it is on the way down, you see the direction of slipping is different. So the direction of friction also accordingly, kinetic friction changes its direction. Okay. So here if I am doing the version while it is sliding up the inclined plane, so its velocity is in this direction at some point of time. So the kinetic friction will act like this. Kinetic friction will act like this, and of course we have components of mg. and we will have normal reaction, and all this together is giving it a deceleration of 10.8 meters per second square when theta is 37 degrees. Whereas while sliding down the inclined plane, the velocity is v like this at some point of time. It will have a different acceleration, let's say a prime, because now friction will be acting like this. So kinetic friction is going against mg sine theta. This will be the case. Okay. So first of all, from this information given, okay, so that implies that kinetic friction and mg sine theta acting together in the same direction is giving you me. So okay, so while sliding up, the rate of deceleration becomes g into sine theta plus coefficient of kinetic friction into cos theta. Okay, so when we substitute this value as the given one 10.8, so 10.8 we'll take the value of g as 10. Should have mentioned that this is 0.6 plus mu k into 0.8. When we do this calculation, we will get the coefficient of kinetic friction as 0.6. Yes, Devansh, correct. Both the answers are correct, second and third part. Pratish, hope the free body diagram is clear to you for the case when it is sliding up the inclined plane. Okay. So then maybe some calculation thing, just check it out. Okay. Now on the other hand, while sliding down the inclined plane, you can see that friction and mg sine theta in opposite directions. So it accelerates at some a prime. Okay. This was the given deceleration. So mg sine theta minus kinetic friction is ma prime. So the rate of acceleration, so when you substitute this over here and theta of course as 37 degrees, you should be getting a prime as 1.2 meters per second square. So interestingly, a prime is as less as a by 9. You can see here the rate of deceleration 10.8 is 9 times the rate of acceleration while coming down. Okay. So that's your second part's answer. Now for the third part, just use kinematics. Third part, int is use this relation that v square is equal to u square plus 2as kind of thing. That's the easiest way of solving. Okay, so got the last part now. So for the third part, can directly use this that, let's say t equal to 0 when it started. Okay, so at that point of time it's decelerating at the rate of 10.8 meters per second square. So it goes up decelerating till at some instant of time t equal to t1, let's say, it comes to rest momentarily. So during this time the maximum displacement upwards, this is such that 0 square is equal to u square minus 2a into maximum displacement. This is our first equation. So we are getting, okay, this is the first equation. Now the second part of the journey, when it is now coming back down from there, and at some time t equal to t2, let's say, it crosses this with some velocity v, but now on the way down it has an acceleration of 1.2 meters per second square. Okay, so for the second, and then also the displacement will be the same, it will have the same magnitude. Okay, so this time v square will be equal to 0 square plus 2a prime into the same magnitude. Okay, so v square is equal to a prime s max. So substitute this over here. So you'll see that v square is equal to 2 times a prime into u square by 2a. So you can see that v is equal to u into square root of a prime by a. Now a prime was 1.2 and a was 10.8. So a prime by a is a factor of 1 by 9. So that is why you will see that v will come out to be u by 3, or v will come out to be 20 by 3, or you can approximate it as 6.67 meters per second square. So minimum calculation, you don't have to find this maximum displacement numerically and substitute and all that. You can just eliminate that term, but this is your final answer. Yeah, sorry, U was 20, that's correct. Okay, so hope this question is clear to everyone. Okay, now let's move on to another type of problem before we return back to those two block type of situations. Okay, I'll scroll up. Wait. Yeah, this part, Prachi. Okay, and third part is also done. Okay, good. Now next example we have this situation. There's, let's say, a vertical wall which is rough, and it has a common value of static and kinetic friction given to us, 0.6, and g is 10 meters per second square. Now there is a block of mass 10 kg, and what we are doing is initially we are pushing the block, or keeping it pinned against the wall by application of an external horizontal force. So an external horizontal force, normal or perpendicular to the wall, is applied on the block as shown. Find its acceleration, that is the block's acceleration, if any, and all contact forces on it due to the wall if the magnitude of this force is 200 newtons, and B, if the magnitude of the force instead of 200 newtons is only 100 newtons, each case. Okay. So you have to find this out, and also the minimum force needed, the minimum magnitude of F external needed to keep the block in equilibrium at rest. Okay, so just try out this question, people. Start with part A and B. So basically, you have to make the free body diagram. From that, understand what is the normal contact force. From that, understand what is the limiting friction available. Now, if the limiting friction available is sufficient to prevent the tendency of slipping, here what is given the tendency of slipping? It is the weight mg downwards. So if limiting friction is able to balance mg, then of course it will keep it in equilibrium, and if not, then kinetic friction starts acting and the object starts sliding. So even as we are pushing it against the wall, it will be sliding vertically downwards. Yeah, so that's correct. In the but only though one thing you have to be careful about is the amount of friction. Okay, in the first case, the acceleration is zero, no? So that means what is happening? The static friction acting is balancing the weight, no? So how can it be larger than weight, no? Limiting friction can be larger than weight, but the actual amount of friction acting cannot be larger than the weight, no? Because then the block should accelerate upwards, no? So yeah, okay, and also you have to tell the normal reaction also. But yes, your answers are correct otherwise. So you realize that what's happening in the first case is the normal reaction being 200 newtons. The maximum static friction available to us is zero point 0.6 into 200 or 120, which is more than the weight. So there is the equilibrium condition. Whereas in the second case, the maximum friction available to us is only 60 newtons because the normal reaction will be 100. So that is not sufficient to balance the weight. So what will happen is that it will be in the slipping condition. So the first case acceleration will be zero. E part acceleration will be zero, and it will be in equilibrium, whereas second case it will be slipping. Yes, Devansh, your answers are correct. Good. Viraj, correct. Okay. So Pratyush, what you have to remember here is that friction cannot create slipping, ना? Friction will oppose slipping. So अगर मेरे पास फ्रिक्शन का जो लिमिटिंग वैल्यू है वो वेट से ज़्यादा है ना, if it is more than sufficient to balance the weight, it exceeds, then the amount of friction acting will not be its limiting value. It will just be the amount that is required to balance. No, no, horizontal force is not balancing, Shikhar. Obviously, horizontal force cannot balance vertical force. It's a logical thing only. What is balancing the vertical force of mg is the vertical force of friction only. Beta. Mg is downwards, but it's a rough surface now. So see what is happening. The moment we apply this external force, we are pushing it against the wall. So what the wall does, it reacts by applying a normal reaction, which balances the external force. Because the wall cannot allow it to push into itself. Na? The wall is a solid object. So the normal reaction in whatever situation, whether it is sliding or not, will balance the external force. Okay. But we have to still see if the vertical forces are balancing or not. So gravity is pulling it down, which means that it has a tendency to slip against the wall. So friction will be acting up the wall. Okay. Now the main thing is we have to see what kind of friction this is. Is this going to be static friction? Is this going to be kinetic friction? So we will see that therefore static friction's maximum possible value is going to be mu into n. So that is going to be zero point 0.6 times F external. So this is our conditional statement. Okay. Now if mg happens to be greater than limiting friction, okay, then it will imply that the acceleration will be non-zero and slipping will occur, and the friction acting will be kinetic friction equal to mu into n. Here mu is common value. Whereas on the other hand, if mg is less than or even just about equal to maximum static friction, then what will happen? Our acceleration will be zero. It will be the no slipping case. And in that case, our friction will be static friction, which will balance mg. So this is very important. And in this case, it need not be equal to mu n, just has to balance mg. So to just check in each of the cases which one is happening. Yes, Devansh, your last answer is correct. Also, yes, Pratyush, second part is correct. First part you understood now, no? Okay, so in A part, the external force we are applying is 200 newtons. So normal reaction is 200 newtons. So maximum friction available is 120 newtons. So you can see that mg is less than maximum. So there is the equilibrium condition. Okay. So static friction will balance mg equal to 100 newtons. Acceleration will be zero. And normal reaction already is this. So this, and this are the three things we were asked to calculate in this part. Whereas in B part, we are reducing this to 100 newtons now. Now, the moment we drop this to 100 newtons, normal reaction drops to 100 newtons. So, maximum friction drops to zero point 0.6 into 100 or 60 newtons. So, we can see now this is the case. mg is exceeding this. So, it's the slipping case. Slipping occurs. Okay. So, in this case, acceleration will not be zero. So, our free body diagram, the vertical case forces will consist of this. You have a downward acceleration E. So friction will be kinetic friction equal to 60 newtons. Okay. Normal reaction already have calculated. Okay. And mg minus kinetic friction will be equal to mass into acceleration. So 100 minus 60 will be equal to 10a. So we'll get the downward acceleration of 4 meters per second square. Okay. Yes, Viraj, your answer is correct for the third part. Now, say C part, for equilibrium, mg should be less than equal to maximum friction. In other words, mg should be less than equal to mu into n, which means mg should be less than equal to mu into F external. So the condition on F external is that it should be greater than equal to mg upon mu, okay, or should be greater than equal to 100 by zero point 0.6. Okay, or it should be greater than equal to 166.67 or 500 by 3 newtons. So this should be answer for the C part. Yes, Pratyush, very good. Okay, people, so hope this is clear now fully. Okay. Now we will move on to a more tricky problem of this kind of concept, a proper JEE advanced level question. Now, this is a chapter in which you can expect questions, actual questions in JEE advanced based on friction and Newton's laws of motion in general. Okay, if you start looking through previous year papers and all that, through many years back also, from IIT JEE to JEE advanced, whatever, you will see that you'll like be able to recognize questions which are solved completely on the basis of these concepts you've learned: Newton's laws of motion, friction, free body diagram method, etc. Only JEE advanced, the difficulty level is generally going to be high. Okay, obviously. So this next problem is of that kind of difficulty level. So we have, once again, this surface is having coefficient of friction the same as this one, zero point 0.6. Now what we've done is we've kept a combination of two blocks like this. So this one is having a mass of uh, 12 kilograms. This surface is having a coefficient of friction of only zero point 0.2, and this one is 8 kilograms. And once again, G is 10 meters per second square. And what we are doing is we are trying to keep the whole system in equilibrium by applying an external force like this. So F external is applied horizontally, normal to the rough vertical wall, to keep the system, that is both blocks, in equilibrium. So first of all, find the minimum magnitude again of F external for equilibrium condition. And second, find the accelerations, if any, of the blocks if the external force we are applying is equal to, just a minute, 360 newtons. Okay, try this out and be very careful while you're solving this. Take into account that you need the equilibrium condition for both the blocks. No, Viraj, answers are not correct, unfortunately. Okay, very good, Viraj. You got the correct answer finally. So far only one person has got the correct answer. Let me put up the correct answers first of all. So this one you should be getting F external should be greater than equal to 400 newtons for equilibrium of both blocks. And this one you will therefore get that equilibrium is not there. So in this case you will see that the block M2 will have an acceleration of A2 equal to 1 meter per second square downwards, whereas the block M1 momentarily will be at rest. This is initially. Of course, when the two blocks lose contact because this one has slipped down, then it's a different situation. So you're not worried about that. Now let's understand how this is happening. So here we have to be very, very careful when we are understanding the free body diagrams. So let's make the FBDs, okay, for equilibrium condition. Then we will get what the condition is for equilibrium. Okay, for equilibrium of both the blocks, what are the FBDs looking like? So block M1, block M2. So we are applying this external force on it. So there is some normal reaction that acts on this. So this applies an equal and opposite normal reaction. So the wall applies an equal and opposite normal reaction. So N1 will be equal to N2 will be equal to F external. Okay, this is the first thing. Then since we are assuming equilibrium, this one's weight has to be balanced by some kind of static friction over here. Okay, so static friction. So F2 has to balance M2G. Okay, so this is static friction, and this one will apply an equal and opposite friction downwards on this. So some kind of static upward friction has to act on this from this side so that weight is balanced. So F1, which again has to be a sort of static friction, has to balance F2 plus M1G. So these are our equations. So we can see that from equation 1, F2, which is a static friction, needs to be equal to 80 newtons, and from equation 2, F1 needs to be 80 plus 120, so 200 newtons. Okay. Now F2 is less than equal to mu2 into N2, and F1 is less than equal to mu1 into N1. Or that is the same thing as mu2 into F external. Or this is the same thing as mu1 into F external. No, F1 has to balance F2 plus M1G. Yeah, and that's correct. Okay, so that's the equation we've written. So let's in fact look at this as a numerical value. So how much was our mu2? The coefficient of friction at this surface was 0.2, and this one at the wall was 0.6. Okay. And between M1 and M2. So this is 0.2 times F external, and this is 0.6 times F external. Okay. So from equation 1, we are getting a limiting condition that F2, which is equal to M2G, should be less than equal to mu2 N2. So this is giving us a condition that 80 newtons should be less than equal to 0.2 F external. So F external should be greater than equal to 400 newtons. So this is like the first limiting condition we are getting. Okay. And from equation 2, we are getting F1 equal to F2 plus M1G. Now this should be less than equal to mu1 N1. So we are getting that 200 newtons should be less than equal to zero point 0.6 F external. So this is giving us that F external should be greater than equal to 200 by zero point 0.6, which you will see is 333.33 newtons. So this is now like a second limiting condition. Okay. So now both limiting conditions must be satisfied. Okay. Both first and second limiting conditions should be satisfied for equilibrium of both the blocks. Okay. So you want equilibrium of both the blocks, both these conditions must be satisfied. So which is the stronger condition? Therefore, F external has to be greater than equal to 400 newtons. That's why the answer to the first part was 400. Okay. So please make a thorough note of this. Okay. We can use a bit of shortcut by making a combined FBD of the two of them to check the condition on F1 on the friction on the wall. But we still have to check the condition for F2, the friction on the block M2, and we have to get the two limiting conditions. One limiting condition is not enough because there are two possible places where slipping can occur. Slipping can occur between the wall and M1, and slipping can also occur between M1 and M2. So we have to check that दोनों जगह पे there is sufficient friction to prevent slipping. So that's why the two limiting conditions have to be checked independently. Okay, so hope this is clear. So we can simplify this little bit, not really by a huge amount, because you still have to write the same number of equations at the end of the day, but can be somewhat easier to understand. But this thing is, you should not make the mistake of making only one limiting condition. You have to check that both the limiting conditions are satisfied, that there is no slipping at either of the two surfaces. So we can also make alternately to check the no slipping condition between the wall and M2, oh sorry, and M1, make a combined FBD of M1 plus M2. Okay, assuming okay equilibrium of M2 with respect to M1. So with that assumption in mind, okay, so we can make a combined free body diagram. So that will give us the way to check the limiting condition on this friction. This has to be static. So it doesn't really save a whole lot of time. Just so we can see that F1 has to balance M1 plus M2G, N1 has to balance F external, okay, and F1 should be less than equal to mu1 N1. Okay, so substitute this here. So the combined weight, this will give you the same limiting condition actually, is F external. So this will give us the condition that 200 newtons should be less than equal to zero point 0.6 into F external. So this will give us that second limiting condition that we had got, greater than equal to 200 by zero point 0.6, or so 333.3 newtons. Okay, but we should not stop at this point, no? Because we have to also justify our assumption that the two blocks are not slipping with respect to each other. Okay, so this is one of the limiting conditions. This is the first limiting condition. But before we can go ahead saying that this assumption is correct, we have to also check for this, that this is not slipping with respect to this. So for checking this condition, check for no slipping between M1 and M2. You again have to make one more FBD. Make FBD of the block M2. So there you will get the other limiting condition. Okay, so this is the same as we have done before. So here you will get F external is greater than equal to this one's weight divided by this coefficient of friction, or 400. Okay. So you get the same pair of limiting conditions. And again, both the things have to be satisfied. So overall, F external has to be greater than equal to 400 newtons for both the conditions. Okay, so hope this is clear. Now this also makes it obvious that in the second case there will be slipping. But you can also see that 360 newtons, it satisfies one of the limiting conditions, doesn't satisfy the second one. That means it satisfies the condition for no slipping between M1 and the wall. But M2 slipping cannot be prevented. So M2 starts slipping downwards and the M1 remains stuck to the wall initially while the two blocks are in contact. So with that now and the new free body diagrams with that relation, you will get the condition that yes, M2 will get detached, but initially when it starts sliding down, no, M1 remains in contact with the wall and therefore it remains in equilibrium. Yes, Rahul, you have some question? Okay, Arya Joshi, have you understood this? Yes, Arya Joshi, have you understood this question? And please tell me the answer of the second one. Also, Soham, Soham Jagdale, have you understood this question? Yeah, Devarsh, you got the answer for the second part. Yes. Yeah, so you'll realize in the second case, what is happening, because the external force is equal to 360 newtons. Okay. So both these normal reactions are 360 newtons. So maximum friction available on this surface is zero point 0.6 into 360. Okay. So that is how much now? 216 newtons, isn't it? And maximum friction available on the second one is only 72 newtons. Okay. So you can see that F2 max is less than the weight of this guy. So M2 slips down. So M2's free body diagram becomes like this. The weight, which is 80 newtons, dominates, so it accelerates downwards. So A2 becomes, yes, that's correct. Okay, M2G minus F2 upon mass. So 80 minus 72 upon 8. So it accelerates with 1 meter per second square downwards. Whereas this one, F1 max, is greater than F2 plus M1G. Sorry, is less than, or greater than, yeah. So that means M1 does not slip. So M1 के free body diagram में क्या होता है? This will be a static friction which will balance the sum of this F2, which is 72 newtons, and its weight, which is 120 newtons. So its acceleration will be 0. So in this condition here, the acceleration is 0, and this friction acting on it, which is static in nature, will be 72 plus 190, 120. So that will be only 192 newtons, whereas the available friction is up to 216. So that again justifies. Okay. The wall is not allowing the block to slip down. The wall is able to apply enough friction to keep the block stuck against it. But M2 is not able to remain stuck because there isn't enough friction. So in conclusion, M1 remains stuck to the wall. Okay. E1 is 0. Whereas M2 slips. So it has a downward acceleration of 1 meter per second square. Okay. So that is what makes this question a little bit more complicated, because there are two limiting conditions within the same question. Arey, Samar, I'm not talking about after they've lost contact. Na? This is the initial moment. You have to imagine the problem. The blocks are there, you start pushing it with this force. No, or let's say initially the force was more than 400, then you reduced it to 360. So क्या होगा ना, पहले एक block slip तो करेगा ना, while it is slipping and losing contact, the other one is remaining stuck. Yeah, it is, and Shikhar, it is clear from the free body diagram. You have to balance the forces. Okay, so hope this question is clear to all of you. Yes, understood ना Shikhar? Forces को balance करना है ना. So the amount of friction required is just, yeah, it's just 192 newtons. We don't need that 216. No. Okay, good. Yeah, so hope this question is clear to all of you. If anyone has a doubt, please send to me. Okay. Now let's move on to some more questions. So now we are coming to the more tricky type of questions, where more than one limiting condition is there. So let's look at another example. Now this time we will revisit the two block problem, but with an additional complication that the floor is also rough. And last lecture when we had looked at the two block problem, we'd seen that situation where the floor was smooth. But this time let's see what happens when we make the floor also rough. So this surface has a coefficient of friction of zero point 0.4, and this surface has a coefficient of friction of zero point 0.6, and m1 is equal to 15 kgs, m2 is equal to 5 kgs, and take g as 10 meters per second square. So first of all, so system is at rest initially. So first of all, find the minimum horizontal force, okay, applied on m1. So what is the minimum horizontal force applied on m1, okay, to make this system move, because there's friction on the ground. Okay. And secondly, find accelerations, if any, for f equal to, So when we apply 100 Newton force horizontally on M1, same thing, F equal to, but this time increase to 240 newtons, again horizontally on the lower block only. Okay, so start with these parts, then we'll also discuss one where we're applying the force on the upper block instead of the lower block. So again, just think very logically when it comes to the direction of friction. Okay, the friction will tend to oppose the slipping. So there are two places where friction is acting. Okay, so be very careful when you're making the individual free body diagrams to try and understand. So just give this a couple of minutes. Try to work out the first part yourself. Okay, so you're getting the answer for the first part, all of you? Yes. Samarth, correct. Devansh, it's less than that. Okay. See, to make the system move, you have to only overcome the friction on the ground. Yes, Viraj, correct. But in second case, they will not have common acceleration, Viraj. Second case, there will be slipping between them. I mean, in the third case, 240 newtons, that case. Okay. So let me put up the answers. Then you can verify also. So you should be getting the answer for this part as F greater than 80 newtons to move the blocks. Okay. Here you will get acceleration of the first block is equal to acceleration of the second block. Whereas here you will get acceleration of the first block not equal to E2. In fact, you will get E2 equal to 6 meters per second square. Whereas A1 will come out to be, just tell you, something like this. Okay, so let's understand how this is working out. Combined weight for the normal reaction, yes, so at the floor. Okay. So N1 you can see is this one's weight, so it's 50 newtons. N2 is N1 plus this one's weight, so it is 200 newtons. Okay. Now the first case possible is that if the external force you're applying is getting balanced with some static friction here. So if F external is less than equal to mu2 N2, then F external is balanced by static friction, okay, between the floor and M2. So then no friction acts between M1 and M2. Okay. This is one case. Okay. And acceleration, और both the blocks is 0. ऊपर वाले ब्लॉक पे कुछ फोर्स ही नहीं एक्ट करता है, and on the lower block. Okay, so for this to happen, F external has to be less than equal to 0.4 into 200. So F external should be less than equal to 80 newtons for this condition. So that is why the answer to the first part, the minimum force needed is just about 80 newtons. It should be slightly greater than 80. So limiting condition will say 80 newtons. Okay, so this part is clear to everyone, I hope. Now see what is happening. If so, this is the case where acceleration of this one is also 0, acceleration of this one is also 0. Okay, so this is no slipping for both. So now the moment F external becomes greater than 80 newtons, what happens? The blocks move. Now as they move, there are two possibilities. They can move together. Okay, so A1 is equal to A2 and friction between them is static friction. Okay, or they can move slipping with respect to each other. Okay, so which of these two is happening will again depend on the amount of force we are applying, the amount of external force. So in this case, A1 is not equal to A2 and friction between them is kinetic friction. Okay. So let us see how we will gauge the condition that which of them is happening. Okay. So again down to free body diagram. अभी मैंने ये जो force लगाया है, suppose this force is greater than 80 newtons. So on the ground, what type of friction is acting? Kinetic friction is acting. Okay. So the moment this F is greater than this has a tendency to accelerate in this direction. Okay. So immediately friction will act on this in the backward direction. Okay. And therefore friction will act on this in the forward direction. And this will have a forward acceleration E1. Okay. So you can see that F1 is equal to M1A1. Okay. And capital F minus F1 minus kinetic friction is equal to M2A2. Okay. In general, this is what will happen, and F1 is less than equal to mu1 m1g. This is a limiting condition. So therefore, we can see that from equation 1, E1, which is F1 by M1, should be less than equal to mu1g. So this cannot move faster than 6. This becomes one very important concept here, that the upper block cannot move faster than 6 meters per second square. So if they are having common acceleration, so therefore, if A1 is equal to A2 and that common acceleration is A, this A should be less than equal to 6 meters per second square. Whereas if A1 is not equal to A2, then A1 will remain 6 meters per second square and A2 will become greater than 6. Okay. So it is from this pair of statements, this one and this one, that we'll understand which of the two is happening for a given particular case. Okay. So now we come to that part, that if we are applying a force of 100 newtons, so you can definitely see that slipping starts occurring. Okay. So now, assuming that they slip together, so assuming M1 and M2 move together, so A1 is equal to A2 equal to A. So we can make a combined free body diagram. So the advantage is we have to only worry about one friction then. And that is the kinetic friction on the ground, which is 80 newtons. Okay. So they have a common acceleration E. So F minus that kinetic friction is combined mass into that common acceleration. So 100 minus 80 is equal to 20 A. So we're getting that common acceleration as 1 meter per second square. Now this is okay because we have already seen the condition that the condition for common acceleration was that common acceleration should be less than equal to 6 meters per second square, this one. So therefore, the assumption is correct. Which assumption? This assumption. This assumption is correct. Okay. And the friction F1 between the blocks is static friction. That F1 equal to M1 into A. You'll see that that amount of static friction acting for acceleration of 1 meter per second square will be only 5 newtons. Whereas the maximum static friction available to us was up to 30 newtons. So again, this is correct. We can see that to prevent slipping, the amount of friction needed, which is 5 newtons, is very much available to us. Because up to 30 newtons of friction is available. But in the third case, if we increase the force all the way to 240 newtons, if we assume common acceleration again, so again from that free body diagram, we'll get this time we'll get 240 minus 80 is 20A. So we'll get A as how much? 160 divided by 20, or 8 meters per second square. Now you can see that this is not possible, because we've already seen that the upper block cannot move faster than 6 meters per second square. Okay, so this immediately implies that there is slipping between the blocks. A1 is not equal to A2, and F1 is kinetic friction. So it's equal to mu1 m1g. So it is equal to 30 newtons. So the moment we understand there is slipping, we have to make the individual free body diagrams. So in the individual free body diagrams, this is kinetic friction of 30 newtons, which will give this an A1. A1 will become 6 meters per second square, as we had expected. When there's slipping between the two, this has to move at 6 meters per second square. But this one will have a larger amount of acceleration. So capital F minus F1 minus the kinetic friction below is equal to M2 into A2. So 240 minus 80 minus 30 will become 15A2. So our A2 will become 160 minus 30. So A2 will become this. So this is the completion of this question. Second part. So please make a note of this, people, and that's it for today's session. So this week, please look to complete HC Verma all the questions. Some of the questions I've discussed today are exactly similar to HC Verma questions, only the numerical values in the question are different. So you will start getting very familiar with those type of questions when you start going through the exercise of HC Verma. So as I said, this week, please try to attempt all the questions from HC Verma's friction exercise. Next lecture will again be a purely problem solving type of exercise. We will discuss HC Verma as well as module questions in that. Yeah, I think next week there is class, no? The Diwali break is after that. Okay, so that's it for today's lecture, people. Wish you all the best.